In the last several videos, we focused on ethers, molecules that have a carbon-oxygen-carbon bond. In this video and upcoming videos, we are instead going to focus on molecules that have epoxide functional groups. We can think of epoxides as specialized ethers in that the carbon-oxygen-carbon bond is part of a three-membered ring. So whenever you see this three-membered ring, it's recognized specifically as an epoxide rather than as an ether. The reason why the epoxide group is a specific functional group of its own is because it exhibits very different types of reactivities than typical ether groups. The reason why epoxides have special reactivity is due to the fact that this three-membered ring creates a great deal of strain due to the fact that it has sp3 hybridized atoms that are locked into a very non-ideal 60-degree bond angle versus the 109.5-degree bond angle that these would ideally be found in. What we will focus on in this video is how we go about naming epoxide molecules. How do we handle a molecule that has an epoxide functional group in the chain, or perhaps an epoxide functional group plus some other functional groups? Before we get started on an example problem for naming epoxides, I first want to go through a couple of pointers to keep in mind. Overall, naming epoxides is going to be very similar to the other types of molecules that we have named so far this semester and last semester, meaning that you'll do things such as find the longest carbon chain, and then once you have found the longest carbon chain in the molecule, you are going to be naming the epoxy group as a branch that comes off of that parent chain. So use the same rules that you've used before to find the parent chain within a molecule, and then the epoxide group specifically are referred to as a so-called XY epoxy branch. And what we mean when we say XY, those are referring to the carbon numbers of that parent chain where the epoxide group is found. And since the epoxide group is found bridging two carbon atoms, that's why we specify this as X and Y. So X would be one of the carbon atoms, Y is the other one. And we're specifying both of those locations where the epoxy group branches off of the parent chain. And we decide how to number the parent chain based on the rules that we've learned previously, where you start from the end closer to where a branch comes off and things of that sort. So you might want to refresh yourself on general nomenclature rules if you haven't already, or if those have gotten a little rusty. So we can think of really naming epoxides as being analogous to naming ethers, except in the case of ethers, the O alkyl group was referred to as an alkoxy branch off of the parent chain, whereas epoxides are referred to as XY epoxy branches. And the X in alkoxy there is just referring to the numerical location of what carbon of the carbon chain does the alkoxy group branch off of. When we think about how we go about numbering the carbon chain within the molecule to come up with the parent name, for numbering the chain to determine the parent name, keep in mind the principles that we learned back in Organic 1 and a little bit earlier in Chapter 14 here, and that is that if there's an alcohol functional group, the alcohol is going to determine the directionality of numbering and what constitutes the parent chain. So you would start numbering from the end closer to the alcohol. Even if there is a halogen closer to the one end of the molecule, or an epoxide group or an ether, start from the end closer to the alcohol when numbering the parent. So number from the end closer to determine the parent. Next up in the lineup of how to determine priority for the numbering of your longest carbon chain, alkynes followed by alkenes. So alcohols take priority if there's an alcohol group close to the end, you start from that end. Otherwise, alkynes. Next up in the list, alkenes, all in priority order. And then you'll notice that alkyl groups, halogens, epoxide groups, and ethers are all tied. They are all equally important in determining how to number the longest carbon chain. And so in that case, what you would do if you have your longest carbon chain is start from the end closer to any one of those functional groups. Don't be thinking that halogens take priority in deciding what end to start numbering from, or ethers take priority. These are all equally important in deciding how to number the chain. So let's apply this information toward an example problem or two. So let's take a look at this example to find the IUPAC name. The first thing that we need to do in determining the IUPAC name is find the longest carbon chain within this molecule. So tracing through the longest pathway through the molecule that I can without lifting my pen or pencil, I find myself looking around here and I can find a longest carbon chain by starting here, for example, coming through the 2 carbons of the ether group, coming down this way would be because it's the longer path through, coming up to here, and then at this point, when I reach where I've left off here with my green highlighter, I have 2 options. I can come upward to here and get a 3 carbon chain 1, 2, 3, or I can come downward to here to get a 3 carbon chain 1, 2, 3. So for our situation here, and for any nomenclature situation, what we want to do is number in the direction that maximizes the number of branches. And so by coming this way through the molecule, we introduce this extra branch right here, whereas if we came this way, there would be no other additional branches. And so maximize the number of branches. If you get to a point in the molecule like here, where there's a tie, meaning that you could come this way to get 3 more carbons, or you could come this way, go with the way that will maximize the number of branches. So coming this way has that extra branch. So therefore, we've come up with our parent chain in green. Then we need to decide the branches coming off of this and how to number it. So I'm going to highlight the branches in pink. We have a methyl branch right here. We have a 3 carbon branch right here, which since it's a linear chain there connected at the end, we call it a propyl branch. We have a methyl branch right here coming off of the epoxide group. Don't forget that methyl branch there, that dash. We also additionally have this epoxide group that I've highlighted in pink. And then finally, we have this methoxy group, an ether group right here that I've highlighted in pink at the end. So this molecule actually has a grand total of 5 branches coming off of it that we need to contend with. And in order to assign the locations of those branches along the chain, we need to come up with our numbering system for the molecule. So for numbering, we're going to start at either this end, the left-hand end of our longest carbon chain, or we're going to start here at the far right-hand end of our longest carbon chain. We decide which end to start with, left versus right, based on which directionality will give us a branch at an earlier location in the chain, since all of these groups are equally ranked. Alkoxy groups, epoxy groups, and alkyl groups all take the same level of priority in deciding how to number the chain. So therefore, start numbering from the end closer to where a branch comes off. And if we start numbering from the left-hand end, we find that a branch will come off right away at carbon number 1. So right here at carbon 1, on the left-hand end of the molecule, we have our methoxy branch. And so therefore, that's going to be what we call position 1. If we started in from the other end of the chain, it would be at position 2, where we have that methyl branch come off. So the better way to number is starting here at the left-hand end of the chain. So we go 2, 3, 4, 5, 6, 7, 8 in our 8 carbon chain. We'll refer to that as octane then as the parent name. So I'm going to sketch out the word octane there. Trying to leave myself lots of room here because we have lots of branches to fill in. And now we're going to plug in those branch names. And I'm going to go ahead and sketch out the names of these so that I can make sure I'm getting everything in the correct alphabetical order. So at carbon number 1, we have a methoxy branch. So I'm going to put 1-methoxy. Then at carbon 2 through 3, we have an epoxide group. So I do 2, 3 epoxy. The epoxide group is always represented by the 2 numbers here that indicate what 2 carbon atoms it is bonded to. So 2, 3 epoxy. At position 3, there is also a methyl group. So don't forget that there's a 3 methyl group. There also is a methyl group at position 7. And so we'd refer to this group as 3, 7 dimethyl. So I'm going to put 3,7-dimethyl. And then finally, we have at position 5 a propyl group, so I'll do 5-propyl. So now we need to arrange these in alphabetical order in the name of the molecule. And so we have epoxy, followed by methoxy, followed by the methyl word there of dimethyl. Remember, we don't use the D and di to alphabetize. And then propyl. So I'm going to arrange those in alphabetical order here as the front part of the name. So starting with the epoxy group, because it comes first in the alphabet, we do 2, 3 epoxy. And then onward to methoxy, 1 methoxy, because methoxy comes next in the alphabet before methyl. Then 3, 7 dimethyl and finally 5-propyl octane. And the word propyl and octane run together as one word there. So 2,3 epoxy, followed by methoxy, followed by dimethyl, followed by propyl, all in alphabetical order. So then the last piece of the puzzle solving here for the nomenclature of this is to fill in the absolute configuration at every stereocenter that we see here. So we have 3 stereocenters in this molecule. We have one here at carbon number 2 that we can assign as RS, another at carbon 3 that we can assign as RS, and another at carbon 5. So we need to plug in the configurations of those 3 locations. So 2, 3, and 5 are the stereocenters, and that's why I've put those here at the beginning of the name with a little space afterward to allow myself room to fill in whether each one is R or S. So at position 2, in order, our highest strength group would be the direct bond to oxygen, followed by the carbon-carbon bond on the right there between 2 and 3, followed by the carbon-carbon bond going between 1 and 2. So that is going to go in a clockwise orientation. The hydrogen at that position is pointed away from us as an invisible dash, and so therefore at position 2 we'd assign that as an R configuration. Similarly, at position 3, we ranked the 4 groups. Highest strength group is going to be that carbon-oxygen bond. Second highest strength group is going to be the bond going over to the other carbon of the epoxide group. Next highest is that bond between carbon 3 and 4. And then lowest ranked is the methyl group. The methyl group is ranked lowest and pointed away from us. So therefore, when the lowest ranked group points away from us and the arrow goes counterclockwise, that is going to mean that it is an S configuration. So at position 3, we plug in S. And then finally, we come over to position 5. And at position 5, ranking those groups, highest ranked group is the bond leading over to carbon number 4. Second highest ranked group is the bond between 5 and 6. Lowest ranked group is that branch to the propyl. And so here we have an arrow that goes counterclockwise, but in this case, the hydrogen points toward us. Whenever the hydrogen points toward us and the arrow goes counterclockwise, that is going to mean that it is R, due to the fact that that lowest ranked group, the hydrogen points toward us in the orientation of this particular group. Lowest ranked group points toward us, counterclockwise arrow, that means R. Now that we've done one example of naming epoxides together, I encourage you to hit the pause button and try to solve this problem on your own, and then use the video to check your work and fill in any gaps in your knowledge. So in solving this problem, what we need to do is find the longest carbon chain as we do for naming molecules. So finding the longest carbon chain, I'm just going to sketch through starting over here, going through the backbone of the molecule. We come to here and we have a question about which direction to go, because going either way, this way versus this way, in both cases will give us one more carbon on our chain here versus here. We choose to go up toward the chlorine because that will maximize the number of branches by creating a chlorine branch within the molecule, whereas if we went over toward the methyl, we would have fewer branches to account for. So maximize the number of branches, so there's 2 ways to go here and coming up with the same length of the carbon chain. Now our next task is to decide how to number this longest carbon chain. So we can number either from the left end, starting here with the alkene group and working our way inward, or we can number from the right end of the molecule, starting here and working our way inward. Now remember from a few minutes ago that when deciding how to number the longest carbon chain, that alcohols take priority over alkynes, which take priority over alkenes. And so when anchoring this molecule to determine how to number it, we start numbering from the end closer to the alcohol group. We have one alcohol group in that molecule. This is right here. And so we're going to number from the right-hand end, going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 carbons in our longest carbon chain here. And now we need to think about what the parent name would be based on this 10 carbon chain, and considering the fact that that 10 carbon chain has coming off of it at position number 3 an alcohol group. So therefore we expect that the suffix for the parent name is OL, indicating that there is an alcohol group, and specifying the location of that alcohol group we will need to do as well. Additionally, when we come over to positions 9 through 10, we have an alkene group. And so we will need to specify that as well by using the term En in our parent name as well, and designating that the alkene group starts at carbon number 9. So filling this information in, the fact that we have an alcohol group and an alkene group, into the parent name of the molecule. The parent name of the molecule is going to follow the template alkenol, where we will specify the numerical location of both the hydroxy group and the alkene group in that alkenol name. So to fill this in, we can do dec, because there's 10 carbons in the chain, and then the alkene group starts at carbon number 9, so we'll call it 9 ene, so dec 9 ene, indicating that there are 10 carbons in the chain. The alkene group starts at carbon number 9, so 9 ene, and then dash 3 all, indicating that the alcohol group branches off at carbon number 3 of the chain. So decene 9 all is what we've accounted for so far. Our 10 carbon chain with alcohol group at carbon 3 and an alkene group that starts at carbon number 9 right there. So then from here, now that we've accounted for the alcohol group and the alkene group, which I've highlighted in blue, we have the remaining branches to denote. So we have a chlorine branch, or a chloro branch as we'll call it, at position 1. At position number 2, we have a methyl branch, and then spanning position 6 through 7, we have an epoxy branch. And so we have to list these based on their numerical location and putting them in alphabetical order into the name of the molecule. So we're going to have 1 chloro, 2 methyl, and then 6, 7 epoxy, because remember that when we're naming epoxides, we name them based on both of the locations where the oxygen comes off of the chain. So listing these in alphabetical order, our chloro is going to come first, followed by epoxy, followed by methyl in this name. So let's go ahead and list that out. So leaving myself some room here, hopefully. 1 chloro, 6, 7 epoxy, keeping this in alphabetical order, followed by 2 methyl, and the word methyl should really run directly into the word dec 9 ene 3 all. So this is going to be our IUPAC name, except for the designation of configuration. And looking at this molecule, we have 4 stereocenters that we need to deal with. The 4 stereocenters we need to deal with are over here at position 2, at position 3 where the alcohol is, and then the 2 positions at position 6 and 7 where we have the epoxide branch coming off. There is no E or Z to assign at positions 9 through 10 because of the fact that at position 10 there is a symmetrical group coming off of that of the 2 hydrogens. So therefore we don't need to worry about plugging E and Z in for our alkene group because that won't be relevant, it won't exist due to the fact that this is a terminal alkene group. But we do have those other 4 stereocenters to assign as R or S. So going to position 2, the highest ranked group coming off of position 2 is going to be headed upward toward position 1 there because of the chlorine coming off at that carbon. Chlorine has a higher atomic number than oxygen, which we would arrive at if we came the other way. So therefore, that's going to be our highest strength group is coming toward the chlorine. Second highest group is coming over here toward the hydroxy group. Third highest strength group is that methyl group. Going counterclockwise with a hydrogen that points toward us means that this will be R. And so therefore I'm going to plug this in as 2R because at position number 2, we're going in the R configuration there. So then we move on to position number 3. At position number 3, highest strength group, definitely going to be that oxygen that's directly bonded there because oxygen has a higher atomic number than carbon. Second highest strength coming over this way toward position 2. Third highest strength group coming over between positions 3 and 4 this way. And so therefore, since the hydrogen is pointed away from us and we're going counterclockwise, this is going to be 3S. Then onward and upward to position number 6, where we have another stereocenter that we need to deal with. At position 6, there's a direct bond to oxygen. There's a direct bond to oxygen, going to be our highest ranking group. Second highest ranking is that carbon that bridges the 2 epoxide carbons. and then third highest ranking is coming over here toward carbon number 5. So this is going to take us in a counterclockwise direction. The hydrogen has to be on a dash here because that's the missing part of the tetrahedron, meaning the hydrogen points away from us. When hydrogen points away from us and the arrow is counterclockwise, that means that it is S, and so I'm going to plug this in as 6S. And then finally over to position 7, highest ranked group, going to be that oxygen that's directly bonded. Second highest ranked group is the carbon bond of the epoxide. Third highest ranked group is coming over here toward number 8. And that's going to be a clockwise arrow. Hydrogen points away from us. So therefore, at position 7, we would say this is R as the complete IUPAC name for this particular molecule. We'll do one last example here of a situation where we have fused rings, where we have a 6-membered ring fused to an epoxy group here. So this is a bicyclic system because the epoxide group was counted as one ring. The hexane ring would count as a second ring. Now, how do we go about naming this? In this case, this particular molecule has 3 branches coming off of the parent ring. When there are 3 branches coming off of the parent ring, or more than 3 branches coming off of the parent ring, the rule for deciding how to number the ring is you want to number the ring to minimize the sum of the branch locations. And this is true anytime you have greater than or equal to 3 branches. And that epoxide branch will count for us as 2 branches there since it's coming off of 2 positions of the ring. And so we want to number the ring to minimize the sum of those branches. And so we can think of a few ways to go about numbering this. We could start numbering based on what I'm showing in blue over at the chlorine atom, coming around to the epoxide. And the sum there, to give you an example of what we mean by minimizing the sum there would be 1, because the chlorine branch is at number 1, plus 3 plus 4 for the locations of the epoxide branches at carbon 3 and 4. That would give you a grand total of 8. If we can do better than 8 in terms of minimizing the number of the sum of branches, then that's going to be a better way to go. So what if we start at the other end here? If we went 1, 2, 3, 4, the sum there is equal to 1 plus 2 plus 4 would be equal to 7. And so the correct way to number this is going to be based on what we've shown in green here, because that gives a lower sum of the numbers. And so anytime you have 3 branches coming off of your ring, this is how you will need to approach that type of situation. So I'm erasing the numbering in blue here because we decided to go with the numbering in green to minimize the sum of the location of the branches. So now that we have done that, what we can do is we can specify the name of this molecule with the parent being the cyclohexane. Remember that word cyclo to indicate that the atoms are in a ring. And then the branches listed in alphabetical order, it would be at position 4, pro branch. And then at positions 1 and 2, we have an epoxy branch. So therefore, we could call this 4-chloro-1,2-epoxy cyclohexane. Then finally, filling in our configurations, we have 3 stereocenters to deal with. They're at positions 1, 2, and 4. At position number 1, our configuration following the arrow that I've put there that's clockwise and the hydrogen pointed away from us would be R. At position 2, on the other hand, the configuration is going to be S. And at position 4, chlorine ranks highest. Coming in this direction is the higher ranking directionality there. Coming this way will give us the 3rd highest ranked group. And with the arrow there pointed counterclockwise and the hydrogen pointed toward us, that means that 4 is going to be R. And so the complete name for this molecule, including the stereochemistry, is what I'm highlighting in yellow here. So with this series of examples and explanation, you should now be comfortable with determining the names of molecules that contain epoxide functional groups in combination with other types of functional groups that we have discussed previously the nomenclature of.